Hello everyone, welcome to another lesson. So in this video, we will be discussing plane areas for polar coordinates. Okay, so graphs with um, polar equations and of course polar coordinates. So let's review polar coordinates. So in polar coordinates, the point is given by r and theta. Okay, so r and then angle theta. So where r, that is the distance of the point from the origin, okay, and theta is the angle that the reference line makes with the positive x-axis measured counterclockwise positive. Okay, so say for example this is our point P. Okay, so r, that is the distance from the origin to that point, and theta is the angle that the this line makes with the positive x-axis. This is theta. Okay, so it is measured counterclockwise positive. Okay, so in areas, okay, involving polar coordinates, so the curves are given in terms of r and theta. Okay, so their equation is usually r as a function of theta. Okay, so for the area, okay, so say for example we have this curve. Oops, sorry. Okay, something like that. Okay, so where this curve is given as r as a function of theta. Okay, and we want to determine the area, okay, of determine the area, okay, bounded by the curve, and from a certain interval. So say from here, which is theta 1, okay, to here, theta 2. Okay, so basically the area that will be bounded by this curve from theta initial to theta final is this one. Okay, so it looks like that. Okay, so in evaluating the area, okay, of this, we will base it from the area of a sector. Okay, so sector, to review what is a sector. So sector is a portion of a circle. Okay, so a portion of a circle. Okay, so say for example we have something like which looks like this. Okay, so this is a sector. So assuming this here is the center, and this coincides with the circumference of a circle. Okay, so bounded by theta. Okay, so review that the area of a sector is 1/2 r squared theta. Okay, so where theta is of course in radians. Okay, so in evaluating the area, okay, of curves using polar coordinates, so what we will do is we will draw a strip. Okay, that way we will draw a strip, okay, in a shape of a sector. Okay, so let's draw our graph again. Okay, so again, say this is our r as a function of theta. Okay, so from This one here, our theta initial, and then here our theta final. Okay, so what we're gonna do is we will draw a strip. Okay, so a strip that is in a shape of a sector. Okay, so this strip now is in a shape of a sector. Okay, so let's say that the radius of the sector is r. Okay, and then this angle, so the angle it subtends is d theta. Okay, so therefore its differential volume, or sorry, differential area is equal to 1/2 r squared d theta. Okay, so therefore if we want to get the area, so we simply integrate both sides. Okay, so that we will have a is equal to, so 1/2 is a constant, so we will have a is equal to 1/2 integral of r squared d theta. Okay, so this is the general formula for the area. Okay, plane area for polar coordinates. Okay, so of course the limits will be determined by the graph. Okay, so theta, in this case we have from theta 1 to theta sub 2. Okay, so but let's not put that in the general formula for now. Okay, so this is the general formula. Okay, and in evaluating this, okay, so we might find the technique of Wally useful. Okay, so we need to also add Wallis formula. Okay, so that we will evaluate the integral easier. So we will review later what is Wallis formula and how to use it. Okay, so for now let's have an example. Okay, so before we proceed with examples for area, so let us first take a look at Wallis formula. Okay, so that we can evaluate the integrals easier later. So Wallis formula works if we have this form. Okay, so product of the powers of sine and cosine, okay, where the limit is from 0 to pi over 2. Okay, so it only works if the limit is from 0 to pi over 2, and the integrand consists solely of powers of sines and cosines. Okay, so here we have m and n as our exponents. Okay, so in Wallis formula, so all we need to do is multiply sort of like a series. Okay, so a series of integers. Okay, so where m, okay, so m is the exponent of sine and n is the exponent of cosine. Okay, so we will start by multiplying m minus 1, okay, multiplied by m minus 3, and then continue that series. So as you can see, we have here a series, an arithmetic series. Okay, so where we have a difference of 2, okay, an increment or decrement of 2. So from m minus 1, m minus 3, then m minus 5, m minus 7, m minus 9, until it becomes 2 or 1. Okay, we stop until the series ends in 2 or 1. And also the same manner, okay, for n, which is the exponent of cosine. So we'll start with n minus 1, n minus 3, and then if that's not 2 or 1, then we continue n minus 5, n minus minus 9, n minus 7, then n minus 9 until it becomes 2 or 1. Okay, and then divide it all by m plus n. Okay, so we add m and then continue again the series of a decrement of 2. Okay, so m plus n minus 2, then m plus n minus 4. So basically it's minus 2, minus 2, minus 2, minus 2 until it becomes 2 or 1. Okay, and then multiply it by a multiplier alpha. Okay, so we have conditions. So alpha is equal to pi over 2 if both m and n are even. Okay, so if both the exponents of sine and cosine are even, then we multiply this whole expression by pi over 2. So if otherwise, alpha is equal to 1. Okay, so when we say otherwise, okay, if one is odd or both are odd, so therefore our alpha is 1. So say for example, so we have this one. So integral of sine to the 8th x cosine to the 4th x dx. So using the Wallis formula, so we will start with m minus 1. So our m is 8. So m minus 1 is 7. Okay, so we'll start with 7 multiplied by 5 multiplied by 3 multiplied by 1. Okay, so you can see the pattern. So 7 minus 2, then 5 minus 2, then 3 minus 2 until it becomes 2 or 1. So you stop there. Okay, so next is n minus 1. So our n is 4. So n minus 1 is 3. So we start at 3 multiplied by 1. Okay, and we stop at 1. Okay, so stop if it becomes 2 or 1. And then in the denominator, m plus n. So our m is 8, n is 4, so m plus n is equal to 12. And then continue, minus 2, minus 2, minus 2. So 12 multiplied by 10, multiplied by 8, by 6, by 4, and then by 2. And then we stop there. Okay? And then multiplied by alpha. So alpha is equal to, m and n are both even, so therefore our alpha is equal to pi over 2. Okay? So I guess we have to use our calculators for this. Okay, so I think unfortunately I left my calculator at the office, so we'll be doing it by hand. So this is, so see the thing, what can we cancel out? So I think the numerators are all odd. Yeah, so we can only cancel 3 and say 6. So this will become 2. Okay, so 7 times 5 times 3. So we have 7 times 3, that is 21, times 5. So 21 times 5, that is 105, I think. Over. So I'm sorry, we can also cancel out another 3, right? So 3 and this will become 4, I think. We can also cancel 5, then this will become 2. Okay, so it will remain is actually only 7 over, so multiply 2 times 2, 4 times 2, that is 8, times 8, that is 64, times 2, that is 128, times 8. So 128 times 8. So we have 64. And then this will become 16 plus 6. That is 22. And then 1024. So 7 over 1024. Okay? So that one. Okay? So, yes, that's it. So notice if we don't use the Wallis formula, so this process will take very long. So this is case 4 under trigonometric transformation. Okay, so because we both m and n are even. Okay, so this will be a very, 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 very long process. Okay, so but luckily we have the very intelligent Wally, so he formulated, okay, so this formula. Okay, so thanks to him, so we don't need to actually transform this trigonometric integral anymore. Okay, but again, this only works if we have a limit of 0 to pi over 2. So another example, so here we have the integral of cosine cube x sine to the 5th x dx from 0 to pi over 2. So using the formula, so let's start with m minus 1. M is 5. So 5 minus 1, that is 4 multiplied by 2. Okay, so 4, then 4 minus 2. 2, we stop if we have reached 2 or 1. And then n minus 1. So our n is 3. So n minus 1 is 2. And then we stop there. Okay, so we are only until n minus 1. And then in the denominator, m plus n. M plus n is 3 plus 5, that is 8. Okay, times minus 2, minus 2, minus 2. So 8 times 6 times 4 times 2 until we reach 2 or 1. Okay, multiplied by our alpha now in this case is equal to 1. Okay, so because both are odd. Okay, both m and n are odd. So times 1. So therefore, this will become, we can cancel 8 and we can cancel 2. So we have now 6 times 4, 24. So therefore, the answer is 1 over 24. Okay, so that's how you apply Wallis formula. Okay, so I think maybe it will be useful later in our examples. Okay, so for our first example, so we have here, find the area of one petal of the rose defined by the equation r is equal to 3 sine 2 theta. Okay, so first thing that we're gonna do is we will graph this polar curve. Okay, so in graphing the polar curve, so we will assign intervals. Okay, so that will represent theta. Okay, so for the intervals, so I would like to use 30, 45, and then 60. Okay, interval. So this is 30 degrees, 45, 60, 90, 120, 135, 150, 180, 210, 225, 240, 270, 300, 315, 330, and then back to 0. Okay, so those are my assigned values, okay, intervals for theta. Okay, so what we're gonna do is to determine r for each of the values of theta. So all we need to do is substitute theta in this equation. Okay, so remember that we are using theta here in radians, so therefore in your calculators, so you must set it to radians mode. Okay, so at theta is equal to 0, so substitute it there. So using your calculators, so you will get the following values. So 0, At pi over 6, you will get 2 points around 2.6. At pi over 4, around 3. At pi over 6, back to 2.6. Sorry, at pi over 3, back to 2.6. At pi over 2, you will get 0. At 2 pi over 3, you will get negative 2.6. At 3 pi over 4, you will get negative 3. At 5 pi over 6, you will get negative 2.6. And as you go along the way, so you can see that there is a pattern. So here we have 2.6, 3.0, and then 2.6, and then 0, and then negative 2.6, negative 3.0, and negative 2.6. Okay, so those are the values of r at different values for theta. Okay, and what we need to do is we need to plot that here. Okay, so I have divided already, so although it's not perfectly divided, so but that will do, because all we need to do is get the general look, okay, of the curve. Okay, so plotting one by one. So at theta is equal to 0, r is equal to 0, so that must be here at the origin. And then at pi over 6, we have 2.6. So we can use our rulers to measure 2.6. So in this case, I will be using 1 centimeter. So 1, 2, and then 2.6 is around here. Okay, and then 3 in here at pi over 4. Its value is 3. R's value is 3, so it's around, let's say, there. And then at pi over 6, pi over 3, we have back to 2.6 around here. Okay, and then back to 0. Okay, so from 0 to pi over 2, so the curve must look like this. Okay, something like that. Okay, so next is from pi over 2 to pi, we have negative values. Okay, so we have here the 2 pi over 3, its r is negative 2.6. Okay, so if it's negative, then it will be measured on the opposite side. Okay, so 2 pi over 3 is here, so therefore if r is negative, we will measure r on the opposite side. Okay, so let's say we have here 1, 2, 2.6, so around here. Okay, and then at 3 pi over 4. Okay, so its measurement is negative 3. Okay, so negative 3 at 3 pi over 4. So it must be here. So 1, 2, 3. So here. And then at 5 pi over 6, this one, it's negative 2.6. So this is the positive side, so the negative side is on the other side. So negative 2.6 would be around there. Okay, so therefore the curve, okay, from 90 degrees to 180 degrees is in here. Okay, and then if we continue that, so from pi to 3 pi over 2, so from here, so from pi, 7 pi over 6, 5 pi over 4, 4 pi over 3 to 3 pi over 2, so it must look like 1, 2, 3, so it must look like this also. So we have positive 2.6. Okay, so let's say it's here, and then the other one is here, so it will look like that. And then last one, so it must probably look like this. Okay, so this is a rose. Okay, so we are asked to solve for the area of one petal. Okay, so one petal. Okay, so I think we can get the from the interval from 0 to pi, from 0 to pi over 2. So this interval, okay, so that interval corresponds to this petal in the first quadrant. Okay, so because these are the intervals when we are tracing this petal. Okay, so therefore in our limits we will only consider from theta is equal to 0 to theta is equal to pi over. Okay, so we can now solve for the area. So area of a polar curve is equal to 1/2 integral of r squared d theta. Okay, so our r squared again is our r. So our r was 3 sine 2 theta squared d theta, and since we are only concerned with one petal, okay, of the curve, okay, so therefore our limits is from 0 to pi over 2 only. Okay, so next is simplify. So we have 1/2 integral of 9 sine squared 2 theta d theta from 0 to pi over 2. So we can take out 9 from the integral sign and then evaluate the integral. So we'll have 9 over 2 integral of sine squared 2 theta d theta from 0 to pi over 2. So in this case, you can use trigonometric transformation. So this is case 4, I think. So you can substitute the identity for sine squared 2 theta. Okay, or we can use Wallis formula since our limit is from 0 to pi over 2. So we'll have 9 over 2 multiplied by, so we don't have a cosine. Okay, so we will start with the exponent of sine minus 1 in the numerator. So since this is 2, therefore we will start with 2 minus 1. And then multiplied by nothing. Okay, because we stop at 1. In the denominator, it will be m plus n. We start with m plus n, but we don't have cosine, so therefore we only have 2. And we also stop there because it's already, the value is already 2. Okay, multiplied by alpha. So our alpha is, since we have square here, it's even. Okay, so therefore our alpha is equal to pi over 2. Okay, so therefore our area is equal to 9 over 8 pi. Okay, we have square units. Okay, so but you can also apply the trigonometric transformation. Okay, so for that. Okay,